Thank you, Dave, and greetings to everyone. So this is a continuation from what we started last week. Last week we basically covered electrical fundamentals is the best way I can think of the way to describe them. Today we're going to cover series and parallel circuits, and this is what I like to say is probably the most basic function of the school. It's going to be pretty basic, but again, all of these series are designed to make us better schematic readers, I guess. And what I do on a day-to-day basis is I look at not just the type of schematics our control panel division produces, but a lot of other schematics from a lot of other manufacturers, and some are easier to read than others. Hopefully, this course, the next couple more weeks after this, that it gives you a little bit better understanding. So I'll just go on and get started. So we're going to cover series circuits first. And again, as I said last week, this class was really designed to be a hands-on class. So with our current situation and what's going on in our world these days, we're going to do our best to kind of convert it online. So in figure 119, demonstrate that 1 volt applied to a circuit with 1 ohm's resistance, that 1 amp will flow. And we touched on Ohm's law last week. And for those of you who are new and didn't tune in last week, or just for a refresher course, I'll tell you what I will do. I will back up real quick and give you an example. And I'm sorry, I am going the wrong way, I do believe. Let's see if we can't back up. Give you a quick review of Ohm's law. E over I equals R. So again, if we're trying to find our voltage will equal I, our amperage times our resistance. If we're trying to find our amperage, I for impedance equals E voltage divided by R, our resistance. And if we're trying to find the resistance, is equal to E, our voltage, divided by our amperage. And this works in all cases pretty close, actually. So what we're not going to have today, and I'll just keep this screen on if y'all can still see okay. What we're not going to have today okay, got it straight. What we're not going to have today is we're not going to have the abilities to actually build these circuits and measure them out with a voltmeter. So, definition, a series circuit is a circuit that devices are connected end to end so that the same current flow through each device. So, from our symbolism last week, if this is our battery and we're flowing out of our positive side through our first resistor, our second resistor, our third resistor, and returning back to our ground of our battery, we're going to have the same amount of current flow through the whole device. We're not going to actually see too many series circuits in our control panels in our industry. Now, maybe we might see more of them on a circuit board level, but I felt like it was the basic and that we should start with this. So, laws of a series circuit. The current flowing through the circuit is the same at any point. That is true. Individual resistance in the circuit is added up for the total resistance. That is also true. So if this is a 1,000 ohm resistor and a 1,000 ohm resistor and another 1,000 ohm resistor, we have 3,000 ohm resistance, or we could also say 3K. K stands for 1,000. The sum of the individual voltage drops equals the applied voltage or source voltage. That is also true. We'll key in more to that as we go through today's lesson. So let's talk about dynamic voltage for a moment. Dynamic means the actual voltage across the voltage source with a load connected. So if you tuned in last week, we talked a little bit about voltage potential and how it can trick you with modern day no load meters. So dynamic voltage is that's the actual raw voltage where we have power behind it. Just kind of think of it like that. Source voltage, the voltage source is not connected to the load. So there is a little difference between these two. They both mean kind of the same thing. Yep, source voltage and dynamic voltage, but dynamic, again, is across the voltage source with a load connected, while source voltage is independent. So no different than, is my battery hooked up or is my battery not hooked up to the circuit? Any questions on this? Okay, also last week I told you, I showed you examples of Ohm law, and we touched base on it just a little bit. And I told you that in some modern day cases, some people that just couldn't stand it had to substitute some of the symbolism. So in this case, in this example, you can see that they substituted the E, which stands for electromotive force, but is voltage. Somebody's replaced it with a V symbol for voltage. I get that, and if that makes people happy, I'm okay with that too. They still kept the I and the R though. If they were really going to do that, maybe they should have replaced the I with an A. Okay, so I'm going to skip over this section for time restraints. This is where I would teach students that we're fixing to build some circuits in the classroom, how a breadboard works. That said, if for any reasons that you want to go out after this class and purchase a breadboard, you can pick them up online very, very cheap. You can actually pick up little science projects for kids at Amazon that come with a lot of other cool things that where you can build your own projects on these breadboards. The breadboard did come from a very, very old term. When people were doing electrical experiments, they would use an actual baker's board that they used to cook bread on, and they would put nails on it or brads on it, and they could build their own electrical projects. This stems like back into the 1800s. So with that, I'm going to kind of skip through that real quick. There's no sense being that we're not going to do these projects and showing you how to actually use a breadboard today. If you buy one, it'll come with instructions. So in project one, we're going to simulate and build a simple series circuit. And of course, we can't build it, but we're going to review it. So we're using a 9-volt battery source for our source. So any calculations, use 9 volts. If you want to work out calculators with this, I do encourage that. We're going to build the circuit where we're routing positive power from the 9-volt battery through a 1,000 ohm resistor, or we could just as easily say 1K. And please disregard the notations here where it says R1. I mean, that could be resistor 1 or F5. Again, some of this information kind of came from sources that I was able to copy and paste to build this. The second resistor that we're going to route our voltage path through, our circuit path through, is another 1,000 ohm resistor. So we're going to have two 1,000 ohm resistors in series to complete a completed circuit. So we instruct the students to build this on their breadboards. We encourage them not to power it up at that time because we want to actually check it with a meter. So resistance at point 1, and that would be this point, or from the wire that's going to connect to the battery, but resistance from this point and this point, -1, shows to be, if we just add these two values up, 2,000 ohms, or we can write it out as 2K. So we instruct the students to verify that with their digital volt ohm meter. So here's where we have a little fun. We can use some Ohm's law to work out some of these calculations, and I encourage each one of you to get your calculators out now on your phone if you hadn't already done so, and let's do this. Series circuit laws. The current flowing through the circuit is the same at any point. If we measure that with a meter, that would be correct. Individual resistance in the circuit is added up. We've already done that. So 2,000 ohm, or two 1,000 ohm resistors is going to equal 2,000 ohms. The sum of the individual voltage drop equals the applied voltage or the source voltage. So we're going to do our best if we can answer this. So what is the current flow in the circuit? Calculated, measured. So if we have 9 volts, I'm going to have to write this out. We know we have 9 volts and we know we have 2,000 ohms resistance, correct? So what we want to do is we want to find out what the current flow is. So does anybody care to take a crack at that? And I'll tell you what I'll do. I'll jump backwards real quick to Ohm's law. Okay, so if I don't have any takers, I'll just work it out for you. So what's the current flow in the circuit? So we're going to start out with voltage of 9, and we're going to divide it by a resistance. And I'll just work it out on my calculator real quick. I have to work everything out longhand. I can't do things real fast in my head. So if I take 9 and divide it by 2,000 ohms resistance, now I can't write 2 for 2K. I have to spell it out the whole way. It equals 0.0045 for our amp draw. So calculated would be 0.0045 amps. So what's the voltage drop across resistance 1? So what we're looking for is, as the voltage, 9 volts at the battery, we're going to see some voltage drop if we measure the meter between the negative post of the battery and right in between the 2 resistors. So remember, if we're trying to find voltage, that's going to be the amperage times the resistance, or at least it should be. So what we're going to do is we're going to take amperage, 0.00045, and see if I wrote that down right. Voltage 9 volts divided by 2,000 ohms equals, I'm sorry, I knew I put another decimal in there, 0.0045. So now that's our known amperage. So if we take 0.0045 and we multiply it by 1,000 ohms, we can expect that our voltage drop across the first resistor is going to be 4.5 volts. That's starting to make sense a little bit? Half of 9 volts. So what is the voltage drop across resistance 2? It would be the exact same. So if we total our voltage drops, we're going to see that we add right back up to 9 volts. Any questions so far? Series circuits are pretty simple. Okay. So if we disconnect the battery and install the meter to check the current flow, this is where we would actually use our amp meter to try to measure the amperage of it. What the students would always find is there was always a little bit of drift, meaning they'd work out the math formulas perfect for this circuit, but when they started applying their meters and measuring these circuits, they're going to see that they're close to the math formulas, but there's always a little bit of drift. Now that's a few things can get kind of into the mix there. One, you got 12 students in a room using a 9-volt battery. Some of those batteries may only have 8 volts on them. They've been used, they've been in storage for a while, et cetera, et cetera. So that's one factor. Another factor is the resistance of their wires that they use to build the circuits has to be applied to the calculations and theory of the whole overall circuit. And then the last thing is the resistance, the value, the percent of efficiency of the resistor or the quality of the resistor. Remember, when we covered last week a little bit about how to calculate certain things about a resistor as far as by looking at the color of the bands or the markings on the resistor. There was also a tolerance. So some resistors, even though it says it's a 1,000 ohm resistor, if you measure it, may not actually be a 1,000 ohm resistor. It may have a little bit of a tolerance drift to it. There's another factor that falls into place is temperature. Generally, when you apply voltage to a circuit, there's a little bit of heat with these resistors that's created. And as the resistors heat, the more they heat, the more we'll see the resistance come up. So it was a lot of fun going through the class to actually build these circuits, work out the math to one point to see what we expect we would see, as well as to turn around and then measure it and see how much it's off. One thing that we would do with the class 2 is extend it a little bit further to see, well, wait a minute, can we figure out why is it this far off from our calculations? And generally the students would always find the problem. It was a bad connection or generally a low voltage battery. Most of them had the same type of resistant tolerances on all their lab projects. So that gives an example of one simple series circuit. I'm going to jump over to the next project or a quick review of this one. So 4.5 milliamps is the correct answer to this total circuit resistance. 1,000 plus 1,000 equals 2,000. Ohm's law, 9 volts divided by 2,000 equals 0.0045 amps. This translates into 4.5 milliamps. Now, if we write it out longhand, 0.0045 amps, if we want to write it shorthand or translate it into milliamps, there's the symbol for it, 4.5 milliamps. So the current is 4.5 milliamps through the entire circuit. So don't remember, the current stays the same through a whole series circuit, it doesn't change. If you know this, you can multiply the amp value by the resistance, and that's what we just did in the last math formula I worked out to calculate the voltage drop across resistance 1. So there's the math shown out. The amperage, 0.0045 amps times 1,000 ohms equals 4.5 volts. You measure the current, measure the voltage at points 1 positive and 1 negative with the battery connected to the circuit. After adding the sum of the answers 2 and 3 together, the measured value and the calculated value should be the same. So again, 4.5 plus 4.5 equals 9 volts. So if somebody only had 8 volts on their batteries, maybe their math or their measured value actually only equaled 8. But if they went back and started measuring the circuit, they would see that they had 4 volts across each resistor rather than 4.5. So the sum of the voltage drop should equal the dynamic voltage. That is always true. Your answers may have been no. This is because the actual values were not exactly the same, but they were very close. And that falls right in line with what I just said about the tolerance of the resistors, the heat of the resistors, and the voltage level on the actual battery. So we're going to go through and do one more, but I'm going to kind of pick out one that's a little bit different. So this is another circuit almost exactly like it, except we've substituted in 10,000 ohm resistors. I'm going to skip it. This is one that's a little fun because we have 2 different resistance values on it, and I think it'll be fun. So they're going to replace the first resistor. First resistor is going to remain a 1,000 ohm resistor. And the second resistor is going to be a 10,000 ohm resistor. And we're just going to, we're going to kind of work this project out a little bit. So the current flow in the circuit, if we have 9 volts, and we have 1,000 ohms plus 10,000 ohms.
A lot cheaper than they are up here.
Oh yeah.
Oh yeah. I think somebody might need to mute their microphone.
I'll take
we'll
care.
get a total of 1,000 ohms for the whole circuit. So now we can do the same exact math. We can take our voltage and divide it by 11,000 ohms. Again, I wish, this is where I really need somebody like a volunteer to chime in here, but I can do this 9 times 11,000 ohms. There's not much amp draw here. 0.00081, and we'll just round it off and say 81. That's close enough. So the current flow is 0.00081 ohms. Now remember, if we want to convert that to milliamps, we would move our decimal places 3 points, so it's 0.8 milliamps is another way to call it out. So the first resistor is just a 1,000 ohm resistor, and we want to calculate what's the voltage drop. We take the amperage, 0.00081 amps, multiply it by our resistance, which is 1,000 in this case. We'll go on and work out the long math here.
Just full of shit.
So the voltage drop, I'm coming up with 0.81. Is anybody coming up with a different answer? I'll wait for just a moment. Anybody working this out in on their paper?
Hey, John, this is Greg. Let me pull up my calculator here.
So remember, E over I equals R. So the question is, what is the voltage drop across resistance 1? So we know what.
0.8182.
Okay, yeah. So you didn't round off the way I did, but yeah, 0.81, right? So that's what the voltage we should see. So what is the voltage drop across resistor 2? So remember, it was a 10,000 ohm resistor. So same problem, or same amperage, 0.00081 amps times 11,000.
$8.182.
Yeah, that's what I got. I got 0.891. What did you say you had? You might need to unmute your microphone for a moment. So the fun part is, if we take the two, so I came up with 0.891. So if we add those two up, 0.891 plus 0.81, 0.891 plus 0.81, I'm coming up with 1.7. Oh, so in the first two circuits, the voltage drops were equal. In this third circuit, the voltage drops were proportional to the size of the resistors. Note that the voltage drop continues to add up to the dynamic voltage. So we started out with 9 volts, and somehow I ended up with 1.7 volts. So let's take the time, and I believe we have plenty. Let's rework this and make sure we're actually doing it right. So we know that we have 9 volts as our battery source. We know from doing the basic math, 9 divided by 11,000, we should be equaling 0.00081 amps. Let's go back and double check our formulas and make sure we're doing it right. So we want to find our amperage. So amperage equals our voltage, which is 9 volts, divided by our resistance. So we've just qualified that first check. Here we are, back to our original one. Okay, so we know that our amp draw is 0.00081 amps. Now what we want to do is redouble check what our voltage drop is across resistance 1. So we have 2 resistors, a 1,000 ohm resistor, and we have a 10,000 ohm resistor. So again, to double check that math formula, what we're going to do is go backwards. And I apologize for going backwards and forwards, but I think this is worthwhile to work out. Oops. So to find our voltage, it's our amperage times our resistance. So if we take our amperage, .00081 times 1,000 ohms, 0.81 is our answer. To find our voltage drop across resistance 2, it should be the same formula, which is 0.00081 times 10,000, and it's 8.1. So there was my mistake. I wrote earlier 0.891. It is 8.1. So now, if we total out 8.1 plus 0.81, we get, let me double check that, 8.1 plus 0.81, I'm coming up with a total of 8.91. And again, that's because I rounded off. Originally, my first amp calculation was 0.0008181. It carried out a few times, and I rounded it off. So that's why I lost voltage. So had I not carried it over or rounded it off, we would have come right back to a perfect 9 volts. So there's proof that, hey, if we get off in making our math calculations a little bit, we can make a mistake. But if we know and understand that Ohm's law is Ohm's law, and it always comes up with the same answer, we identified we didn't have values working out, because when we added our voltage drops back up together the first time, we came up with 1.7, and that was not right. We went back and reworked it, found a mistake that we made, and we added everything back up, and we were just under 9 volts, which is where we should have been if I had not had rounded off my very first calculation on figuring out what the amp draw was on the total circuit. We would have come out with a perfect 9 volts again. And that's kind of proof in the pudding that Ohm's law does work. Any questions? So let's do one more just for fun. These are always good exercises, even for me. Let's take this last circuit, Project 5, go with a 9-volt battery again. This time we're going to use a 100 ohm circuit, a 10,000 ohm circuit, resistor, and another 1,000 ohm. So if we add those up, 100 plus 10,000 plus another 1,000
11,100.
Thank you. So not much difference. So now let's take and calculate what our total amperage will be for this circuit. So again, that's going to be 9 volts divided by 11,100. I'm coming up with, and I'll call it all the way out this time, I won't round off. I'm coming up with 0.00081,081. So now if we use that number, 0.00081,081, and we multiply by our first resistor, 100, come up with an answer, 0.081081 volts. And if we do the second resistor, so again, we start with 0.00081,081 amps. And I'm sorry, I made a mistake. I'm supposed to multiply. Times 100. There we go. And it is easy to make a mistake when you're doing this. 0.081081 if we multiply. Okay, maybe I did multiply, but I wrote down a division signal, sorry. All right, so the next resistor, 0.00081,081 times the next value in line is 10,000. We get quite a bit of a voltage draw, 8.1081. And let's do the last one, 0.00081,081 times 1,000 ohms. I'm coming up with an answer of 0.81081. Not much of a voltage. So I want to point out something too. Our biggest resistor is the 10,000 ohm resistor in this circuit, and also shows that, hey, we had the biggest voltage drop across it of 8.1, where the rest are not even a volt. But if we add everything back up, 0.081081 plus 8.1081 plus 0.81081. I'm off just a little bit, but 8.999991 volts. So again, modern day calculators aren't even perfect. Does anybody see the benefit of knowing this information?
So this would be good if you've got some kind of circuit set up and you've got problems, low voltage, and maybe you realize that you've got voltage drop maybe in the line coming over to your circuit. It's not just the circuit. So if you add them all up and you can't find some voltage, maybe, oh, I need to go put an ohm meter on this wiring run, and maybe I've got a a burnt wire or something. That's one application I would think.
For me personally, if I'm trying to figure out something about a voltage drop or a ground potential loop problem, something like that, very valuable. Do I use this information every day? Absolutely not. Series circuits aren't very popular or very common in our industry. But what I do find valuable about it is the exercise, and this is why we use it in the class, the exercise of understanding how characteristics of the circuit link up with Ohm's law and how they work and how they can calculate it. Besides what we can dream up to do in a classroom environment, if we know this information and know it well, we can apply it to real world situations. And I did one of the best examples last week is where we use Ohm's law on a regular basis to calculate what we're doing with some of the circuits where we're taking a milliamperage signal, but we're converting it to voltage so a computer system can read it. There's not a computer system in the world out there, a car ECM, a Allen Bradley PLC, an Altronic product is no different, where we truly measure amperage from, say, a pressure transducer. In everybody's case, what they do is they take a pressure transducer that might be working on amperage on a 4 to 20 milliamp current loop, but everybody sooner or later converts it to voltage ultimately, and some of them are not that forthcoming as far as how they do that. We are very open in what we do and the products we do. In fact, whenever we're converting, we use either a 200 or a 250 ohm resistor, and that's it. The purpose of this class, more importantly, or this exercise in this part of the class when students are hand-on, is the practice of reading a schematic, as an example of this one, and then building it. And you'd be surprised how the different schematic, every student's going to wire up something totally different from one another. So you can put 12 people in a room and you're going to get 12 different layouts on these breadboards. But the correlation of being able to read the most simple schematic in the world and laying it out and building it, and then dissecting it both with an actual physical voltmeter to verify some of the values, as well as taking the time to work the math the way I just demonstrated in a couple of examples, is pretty valuable. It also helps us as we get further down into the class to understand how to read schematics and apply them. So with that, what I want to do is I want to jump over to the parallel circuits. Parallel circuits are real tricky. They work in a total different way. I'm going to stumble. I'm going to need several people to help me work on the math here because I am using the student version with no answers in it for today's class. I guess I woke up this morning and wanted a challenge. So a parallel circuit is when all positive terminals are connected to a common point and the negative terminals are connected to another common point. The voltage applied on the circuit is the same across each component. So think about that statement and let me kind of continue to walk through and show the schematic. So I have a voltage source here. I have a positive rail here, and I have a negative rail here. And I'm going to refer to each one of these as a rung in the schematic. So I have amp draw going through each one of these. So let's look at the laws for a parallel circuit. The voltage is always the same across each branch. So if I've got 9 volts here and I measure voltage here, 9 volts. If I measure voltage across this one, 9 volts. If I measure voltage across this one, 9 volts. So yeah, I believe that law. I'm not going to get a voltage drop across this first resistor and it's not going to affect this resistor or this resistor. The total current is equal to the sum of the individual branch currents. The total current for the whole circuit is equal to the sum of the individual branch currents. So we're talking amperage here. I tell you what, we'll work at least one of these and we'll see if that's true. The total resistance is always less than the smallest resistive branch. Think about that. If I measure resistance from this point to this point, the total resistance is always less than the smallest resistive branch. Makes sense. And we'll see if we can't answer that and make everybody understand that here in a minute. So again, there's our Ohm's law formula. Give you a chance to write it down if you hadn't already done so. And we'll go to the first project. And it looks pretty simple. So what we've got right here is a very, very simple circuit, 9 volts. Our first branch or leg of parallel circuit is 10,000 ohms, and our second one is 10,000 ohms, so they're both equal. So what we want to do is we want to build the parallel circuit in this figure on your breadboard and don't apply power at this point. Both resistors are equal, so the current has 2 paths to travel from equal resistance. What should the total circuit resistance be? And we kind of answered that, but we hadn't answered that yet. I need to pause for just 1 second. I do apologize. So what we want to do is we want to measure the resistance with our digital volt ohm and record the reading on the next page for all the questions. Well, obviously we can't do that, so we're going to have to work out the math. So I'm going to have to skip this page and kind of give the answers to the questions that have already been asked. So we remember on a series circuit, you would simply apply the resistance value to get the sum of a total resistance. So resistor 1 plus resistor 2 plus resistor 3, so on and so forth. It's more complicated in a parallel circuit. When the resistance are combined, the total circuit resistance is reduced. So think of this as water flowing. We talked a little bit about that last week in comparison when we tried to talk about voltage and amperage and we compared them to a water hose, so to speak. So all of a sudden, if I've got one source and one destination, but yet I start doubling up the amount of water hoses, my resistance goes down and I can actually flow more if we think about that. So when resistance are combined, the total circuit resistance is reduced. The larger the number of paths for electricity to flow, the easier it is for the source voltage to push the current through the circuit. So this is where I do talk about water again. Think about 5 gallons of water tank with 2 valves on it for a drain. If one valve is open, it will drain all the water out. Sure, it'll get there. But if both valves are open, all the water will drain out twice as fast. Well, as long as the valves are the same size, that's true too. So the law of resistance is the same in electrical circuits. As resistances are combined in the parallel, the total resistance decreases and the total current flow increases. So this is where parallel circuits can get really, really tricky. To calculate the total resistance of 2 parallel resistors, use this formula. So resistance total is going to be equal to resistor 1 times resistor 2, then divide that by resistor 1 plus resistor 2. Now, personally, I think a lot of this is a lot more important when people are designing circuits and or especially on circuit boards in electronics like we do at Ultronic. But let's work the math out. So we're trying to find out our total resistance of this original circuit. So remember, let's go back one or two pages. We just have 2 10,000 ohm resistors. So it's a pretty simple circuit to start with. So resistor 1 is 10,000 ohms times resistor 2, 10,000 ohms. We'll divide that answer by the sum of the two resistors. So resistor 1 plus resistor 2, in this case, is going to be equal to 20,000 ohms. Anybody disagree with that one? I hope not. So 10,000 times 10,000, if we work that out longhand, and I come up with right at, looks like 100 million, if I'm spelling it out right. Anybody else working this with me?
I got 5,000 for the total resistance.
10,000 times 10,000.
He's already to the end.
Oh, yeah. Yeah, it's 100.
Oh.
100 million. Yeah.
You jumped to the end on me. Okay. So if I go 1 million or 100 million divided by 20,000, you're exactly right. Yeah, I came up with the same thing. So do you notice anything right there? Something sticks out like a sore thumb to me. Remember the law, if we go back, let's see if we can find that law. The total resistance is always less than the smallest resistive branch. So in this case, we had two resistive branches that were 10,000 in a parallel circuit. And what we saw was that the total resistance for the whole circuit is 5,000, so it's exactly half of that. This is where what I'll do is I'll go into a big old spill about how we can double the resistance value of something, or we can cut the resistance value in half. And if I have a lot of young people in my classes and the situation fits, what we'll do is we'll talk a little bit about audio equipment and speakers. And I'll save that today and won't get there, but think about this. If we are doing a series circuit, and the rule of thumb is that all the resistance values add together, but if we do a parallel circuit, and the formula, in this case with two same resistors, the resistance value is cut in half. All of a sudden, that gives electrical engineers a whole lot of flexibility to play with resistors in different circuits and circuit branches throughout a whole project or a design that they're doing. And that one, I actually use these two factors a lot in some everyday projects that I do sometimes around the house with audio equipment. And it's a lot of fun. But any questions on how we work this formula? So where it becomes more devices is when you get into more complicated circuits. So I want to point out one thing on this circuit here, and we'll probably run through this one. I think we have time for sure. This one actually is starting to look a lot like some of our schematics that we see in an ultronic panel. I have my voltage at the top. I have a positive rail on the left-hand side. I have a negative rail on the far right-hand side. And connecting through each one, I have two different resistors. I could just as easily have a relay coil in here if it's a resistor, or a relay coil with a light. So this starts to look a lot like some of our schematics that we draw for our control panels. But let's work the same formula out on this one real quick. So we have a 10,000 ohm resistor, and we have a 1,000 ohm resistor. So what we're going to see is we're going to see with two like resistance values, we could say, well, hey, if they were both 10Ks, our total resistance for the total circuit is going to be 5,000. This one's going to be a real kicker here, though, because we've got a 10,000 ohm resistor and we have a 1,000 ohm resistor. So if we start working it out, our total resistance, we're going to take a 10,000 ohm and we're going to multiply it by 1,000 ohm. Coming up with, looks like 10 million. And then we're going to add the values of the two resistors together. So that's 11,000. Lester, have you worked out what the total resistance is yet?
909 ohms.
Let's see if I punch the 0 button
Agreed.
just enough time to get the same thing.
Yeah, that's what I got as well.
Yeah, 9,009. Or 909, is that what you said, Lester?
909, correct.
Yeah, okay, that's what I got. So the total resistance is 909. So if I'm not mistaken, 909 is less than 1,000 ohms, right? Yeah, by quite a bit. So you see how that works? So let's see. So this is where, how many of us have ever been, let's try to put this in practical sense. How many of us have ever been measuring resistance on a circuit and we're sitting out there scratching our heads, not understanding why we're getting such an obtuse number? An example is, hey, I have a fuel valve coil, but I know if I take it out and put it on the tailgate of my pickup truck or in the front seat and I measure the resistance by itself, it might be 4 ohms. But now I go and apply it into a circuit with other devices and I'm trying to measure the overall resistance of the circuit, thinking maybe that I'm looking at just that fuel valve, but there's other things that play in the circuit and I'm getting some crazy number. Has that ever happened to any of us? It's happened to me more than once.
You forget to
So,
add a 0 or something, so you know.
yeah, but you think about this. You've got a device that you're trying to troubleshoot out in the field, and this is why this exercise is important. You've got a device out in the field that you're trying to troubleshoot, and you take it out, and it seems like it's checking out okay. And if we go back to last week's lesson, they said when you're measuring the resistance on a component to remove it from a circuit, do you remember that situation? So you're supposed to remove it from the circuit to measure it because you don't want other things in the circuit throwing it off. So you take this device out and you check it out and you said, well, man, it's working great. But then you throw it back in the circuit and it's still not working. Well, something might be wrong with the circuit, obviously, right? But you said, well, let me check the resistance again. And all of a sudden you get this crazy number that makes no sense, but it's not an open circuit either. So this could be what's at play. Is there something else in that circuit when the overhaul wiring harness or the skid wiring going out to the unit, going out to the device that's throwing you off? And if it's wired parallel, there's one of your answers. So that's one of the reasons why I like this exercise so much. And it's a challenge for me every time too, believe it or not. So if we look at this, we say, well, what's the total resistance of the circuit? Well, we calculated that, 909 ohms. What's the dynamic voltage calculated for the circuit? Well, dynamic voltage actually, because we don't have a voltage drop, if we come up here and measure 9 volts right here, if we come right here and here, we're going to have 9 volts. If we come right here and here, we're going to have 9 volts. So I'm going to say the answer would be 9 volts. So what's the current through the 10,000 ohm resistor? So if we break that down, can we add that up? Now the resistance is 10,000 ohms, and we know that we have 9 volts going to it. Lester, you want to take a stab at that one? What's the current there?
I got
Voltage divided by resistance, right?
right. I got 0.0009.
0.0009. Well, yeah, one would think that's going to be what it is, right?
Right.
So what's the current through the 1,000 ohm resistor? Again, 9 volts divided by 1,000. What you got, Lester?
.0090.
0.0090. Now, almost the same thing, just a little bit off, but it makes sense. What between a 1,000 and a 10,000 ohm resistor? But does the total current? Let's look at this next question. Does the total current equal resistor 1 plus resistor 2 calculated? So if we add that up, I just got 0.0099. Does that sound about right, Lester?
Yep, that's right.
Mm-hmm. Is that right?
That's what I came up with.
Yeah, but we did those formulas based on what? Series circuit, right? And see, this is kind of a tricky one here for you.
Yep.
So at this point, what we would be doing is if we actually have this circuit where we are measuring it in front of us, right? And then we're working the math, but we're kind of going back on what we did at the beginning of the series circuit section. We would see that our numbers aren't matching up what we're actually measuring. So we know that our total resistance is 909. So actually, what we do is we take 909 for our total circuit resistance and we work the same formula. So let's see if I can help fill in the piece here. We're not going to have a different current per se on these different legs, but we're going to have a total circuit current, right? So to find that current, we're going to take our voltage, which is 9 volts, and we're going to divide it by our total resistance, which is 909, correct? And actually, I came out real close. I did. I hit the nail on the head. Guess what? You're right on spot, 0.0099. Did y'all see that? Did you work it out too, Lester?
Yeah, I did. I did the Ohm's Law deal, and that's what I came up with.
Ain't that funny? So we sat there and we calculated what our current through resistor 1 should be and resistor 2, which in one case we got a 10,000 ohm resistor, in one case we got a 1,000 ohm resistor, and we're thinking, no, we're not going to have the right number. But then we take our total circuit resistance, our total resistive amount, which was 909, and we did the same formula virtually. Yeah, we did. Voltage times resistance, and we came out with the same answer. So we calculated it individually. We added it up, and we came out with 0.0099. Then we calculated it again the same way, but using our circuit total resistance, and we came out with the same answer, 0.0099. Pretty cool, right? Like I said, I don't claim to be an expert on all of this, but I dig what Ohm's law does because it proves me wrong more than once, and it proves that Ohm's law is truly that, Ohm's law. It always adds up. So when more than two different loads are in parallel, the standard total resistance formula sometimes doesn't work, though. When calculating the total resistance in a parallel circuit with more than two different resistive values, use the following formula. Now, this is where it gets real crazy. I don't expect any of us to sit here and work it all out. But if you retain this information or send me some information, I'll be glad to send you a copy of this. You can have it and have it in your arsenal of math and fun stuff to try. So it does get extremely hairy through this. Like I said, I don't expect any of us to work it out, but an example would be resistance 1 equals 200 ohms. Let's see if we've got a reference here. Apparently I don't show this circuit, but this is an example. Resistor 1 equals 200 ohms, resistor 2 equals 275, and resistor 3 equals 330 ohms. So if we take 1 divided by 200 is going to equal 0.005. Now 1 divided by 200 equals 0.005. And remember, we're getting our 1 here. Right here, here, and here in this formula. We're just working out this formula. 1 divided by 275 ohms resistance, there's our answer, and 1 divided by 330 ohms, there's our answer. So now we take these and we add them. 0.005 plus 0.0036 plus 0.0030, and we equal 0.0116. So now we're going to take 1 divided by 0.0116, and it equals 86.2 ohms resistive total. So to answer question 1 on the previous page, the formula would not work out as follows. Well, we kind of said it did, but let's look at this. 1 divided by 10,000 equals 0.001. 1 divided by 1,000 equals 0.001. So if we add those together, we've got 0.001. 1 divided by 0.0011 equals, hey, wait a minute, that's starting to look familiar, 909 resistive total. So we showed an example here of a different way to work it out from what we did. This is the best way to do it because had our resistance been all over the place, like this example, don't believe we would have been able to get the same answer. So there's just another way of working it out. All right, so in circuit 1, the resistors in each branch were equal to. This provides you with a shortcut when calculating the total resistance. The total resistance equals R of each branch divided by the number of branches. There's another little quick formula you can do. So if the resistance values on each branch of the parallel circuit are the same, you can work it out. 10,000 divided by 2 equals 5,000. So if you had 3 or 4 branches, the resistance would keep dropping down. Does that make sense so far? So if we had 10,000 times 3 branches, we would do the same thing. Let's work that out. 10,000 divided by 3, oops. Do 10,000 divided by 2, we do get 5,000. If we do 10,000 divided by 3, yeah, we're getting 3,000. So every time we add an extra resistor or an extra rung to our circuit, our total, if it's the same resistor, our total resistance is going to keep going down and down and down and down and down. Is it possible to add so many resistors to a circuit that all of a sudden we create a dead short and we start blowing our master fuse? Anybody want to answer that question?
Yeah.
Yeah, it is. So remember we talked about the symbol in Ohm's law, and I wasn't going to do this, but I really want to do it today. Remember when we were talking about amperage last week in Ohm's law uses the symbolization of I, right? Let's see if I can stop sharing this for a minute and give up a whiteboard here. All right. Can everybody see this whiteboard that I've got on the screen?
Yeah, we got it.
All right, cool. So when I was a young person, and I guess I'm kind of still into this, I did a lot of audio stuff, and it wasn't for like playing music, but it was for, well, I guess it was playing music. It had to do with amplification and setting up sound stages. Yeah, I used to be in a rock and roll band years ago. Imagine that. But we started blowing up amplifiers one time at this one thing, and this is where I guess one of my first early things where I didn't know I was figuring out Ohm's law, but I guess I was. If we think about impedance, the symbol, again, they use I in Ohm's law. It stands for impedance, and you'll hear that term in the audio. And I like to use this because it has a direct correlation between what we've just been studying a little bit and trying to understand about Ohm's law, how series circuits and parallel circuits work. So I'm going to say that the goal of this is to create as much noise as possible. I have X amount of power from an amplifier. Well, we know that if we're using an amplifier in the audio world to do what? Make noise. The object of what we're actually trying to do is to move air, right? So let's just say I have a 20 watt amplifier, and I'm going to drive with that 20 watt amplifier one speaker. And let's just say the 12-inch it's a 12-inch speaker. So I move a lot of air with that, right? Everybody agrees with that. 20 watts can move the speaker, flex the speaker, and we move a little bit of air. But if we want to make more noise, we want to try to do everything we can to move more air. So let's just say that the impedance or resistance for the coil on that speaker is 8 ohms. So our amplifier is rated at 20 watts of power at a single 8 ohm load. Right. So our goal is to figure out, and this is why I like to use this. It helps us understand how we can combine series circuits and parallel circuits in a way for our advantage, and we can trick things. Our goal is to move as much air as possible. The more air we move, the louder we make this noise. So now what I'm going to do is I'm going to say, hey, wait a minute, I'm going to bring in more and more speakers. So I've just added 2 speakers over here on this side, and I'm adding 2 more in here. Now these are all still 12-inch speakers, so each speaker is going to move the same amount of air. But if we're combining them, now we're running 4 speakers rather than the 1. See if I can erase this. But I still only have 20 watts. But 1 speaker is going to move X amount of air. 4 speakers is going to move 4 times the amount of air. Everybody agrees on that? But if I wire them up all direct, I could drop, if I wire them all up in parallel, what will I do? A parallel circuit, remember, we dropped the resistance, correct? So what would happen if we did that? Our resistance would keep dropping down lower and lower and lower. While that's great, we eventually drop down so low that we create a dead short, and we do what? We blow out our amplifier, which is exactly what I did when I was about 17 years old. And trust me, that cost a lot of money, and I was not happy about that. So we want to figure out how to keep an 8 ohm load, but yet move more air. So if each speaker is 8 ohms, there's a couple of recipes we can do. Well, the first thing we could do is we could wire these speakers in a series circuit. Now, if I did that, what kind of load does that have? We come in, we have sorry, go ahead.
Isn't it 4 ohms?
Series, remember? We're coming in on a positive branch here. We come out for negative, go into the positive, come out for negative. We add those together on a series circuit, right? So that would be 16. So if we do the same thing over here on this side, we've got a 16 ohm load here too, right? Everybody agrees with that? Series circuits, we add everything together. But we have two same resistance values together. So now, if we wire up just like that, well, now we're moving air with two speakers, but we've just doubled our impedance load to the amplifier. What's going to happen right there? Basically, we just crippled our power. We only have about 10 watts of power. So we didn't gain anything if we wire up like that. Yeah, we're moving twice the amount of air, but we're not flexing the speakers much because we crippled it, because rather than the amp seeing an 8 ohm load, it's seeing a 16 ohm load. But now if we bring this little guy in, do the little hop, skip, and jump, and we wire it in here, and we wire it in here, that's a parallel circuit, right? It's not pretty, I know, but it is a parallel circuit. And so if we divide 16 by 2, we just drop the total resistance of this circuit down to what? Back down to 8 ohms. So we used a combination between two separate series circuits, but then wired the two series circuits back into parallel. We still have our 20 amp amplifier. It still sees 8 ohms as a load, but what does it do now? It's moving 4 times the amount of air with the same amplifier. And each speaker, because of the loading, the way we've wired this up, is going to flex as much as the one speaker by itself. So we're moving, each speaker is going to move the same amount of air as that one by itself, but now we've got 4 speakers doing it. So our noise level just quadrupled. Does that make sense, how we can use the Ohm's law to our advantage to fool certain things?
Yep.
Cool. Let's see if I can get back to our video that we were sharing. Don't build this circuit, let's just use it as an exercise. Okay, this is probably a great one to do. We got time, run through it. So we've got 3 resistors, resistor 1, 2, and 3. And I apologize earlier, I did get a little bit off on some of this other stuff. The formula where we came up with the answer 909 works great as long as there's only 2 resistors in the circuit, but it's when we add 3 or more, it starts getting a little hairy. So we've got 3 resistors, 1, 2, and 3 in a parallel circuit. All resistors are 6 ohms. So exercise 2, resistor 1 and 2 equal 6 ohms, and resistor 3 is going to equal 4 ohms. So if you will, if you have available to you a short little piece of paper, and we'll see if we can't do this together real quick in the time that we have left. Exercise 2, resistor 1 and 2 are 6 ohms. I'm going to draw this out. Resistor 3 is 4 ohms. Exercise 3, resistor is, we got a 4 ohm, a 6 ohm, and a 10 ohm resistor. So the question down here is, what is the total resistance on exercise 1? So if all 6 resistors are the same, let me see if what I'd like to do is get y'all to work the math out here based on what we've kind of covered. And for reference, I'll tell you what, let me jump back right here to this formula here. So I'm taking 6 ohms divided by 3. So 6 ohms. Each resistor is 6 ohms. 6 ohms divided by 3, total resistance should be, anybody want to take a stab at this one?
I'll say 2.
That's what I got. Anybody else?
Yep, that's what I got.
Okay, I agree. Now, remember, we could do the simple formula. We could do the simple formula. Why? Because each resistance was equal. Okay. So exercise 2, what's the total resistance? So we got 2 6 ohm resistance and 1 4 ohm resistor. So I think what we need to do, correct me if I'm wrong, is go back to that more complicated formula. Does that sound about right? When calculating total resistance in a parallel circuit with one or more two different resistive values, use the following formula. So we've got a 6, 6, and a 4. Now we're going to feel like we're all back in grammar school, right? So we work the first part of the formula out, and we get our answers here, which I've got 1666667 for the first two resistors, and I got a 0.25 for the last resistor, 4 ohm. And now we add those values together.
Got 0.57.
Say that value again.
0.57.
Anybody else?
Well, I've got a .583.
I'm almost done. I'm a little slower. I came up with a 0.583 as well. Anybody got anything different? We got a 0.57 and a 0.583. Is there a different value? So now we take 1 divided by 0.583 or 57. Anybody want to share their answer?
Yeah, I've got 1.714.
I got 1.715, so I'm off just 1 digit from you. Oh, well, okay. I rounded a little bit too. I've got some kind of crazy number that carries way out, but yeah, I rounded it to 0.715. Lester, how about you? What'd you come up with?
I got left behind. I had to take a phone call, and so now
That's all right, buddy. I think, hey, we got 2 answers that were right close together, so let's go back to the original question. So all we were supposed to do is what's the total resistance value? So we had we had 2 6s and a 4. And so we're coming up with 1.715 for the circuit total resistance. Let's do the last one. 4, 6, and 10. See if we can find the same answer. And let's just kind of work on it real quick. And when we all get our totals, let's get about 3 numbers and compare what everybody got.
All right, so I've got a .517 for the total.
I got a 2.3 for the total resistance.
Got 1.96.
Or yeah, 1.934 is what I got for the total.
Well, y'all are all faster than me. All right, I'm going to round it too. I'm coming up with 1.9. Is that the consensus of what most of you guys got?
Sounds right.
Yeah. So, parallel circuit. If the resistance on every branch of the circuit are the same, you can use a simple formula. If the resistance on each branches are slightly different, you have to use the more complex formula. Now, in my world, the easiest thing for me to do is I'm just going to get my meter out and start measuring, right? Again, the whole purpose of the main primary purpose of this exercise, the way we developed this class was for the students to have an opportunity to look at a schematic, a simple schematic, practice taking what they see on the schematic and building the circuit. This is first part of schematic reading. But because we're also covering some of the fundamentals from last week, we want them to practice using their meters. We also want them to practice using Ohm's law. So that's the purpose of this whole exercise, is to give you some fundamentals of all these different techniques. So with that, let's see, we might want to look at this last page and see if we can answer any question. So yeah, we all came out with pretty much the same thing, 1.9. Maybe slight different variances. Did anybody come up with something way different than 1.9? No one? Lester, what did you get, just for recap?
Well, I think my formulas, I had 2.06, but it was 12-volt supply, was it not?
Well, we weren't even putting voltage into this. We were just trying to figure out the circuit total resistance. So we had 3 rungs. So that's a good opportunity. Let's work it out. So we were trying to find the total resistance. So we had 3 rungs. Each rung had a different resistive value. The first rung had 4 ohm resistor. The second one had a 6, and the third one had a 10. So what we did was we took 1 divided by 4 ohms, and it equaled 0.25. We took 1, divided it by 6, and that equaled 0.1666667. I didn't round this time. And then we took the last one, 1 divided by 10 ohms, and we got 0.1. We tallied all those answers together, and we came up with 0.516. Then we divided 1 by that answer, 0.516, and that's how I got 1.9. And I did round off on the final answer because I had, I don't know, another 100 numbers behind that 9. Is that way everybody else worked it? Okay, so exercise 3, the total resistance is 1.9. Do we want to figure out what the total current flow is? Sure, why not? Now that we know the total resistance, what's the total current flow? If it's 9 volts, and we got, so that's our E, and it's 1.9 for our total resistance, so that's our I, and we want to find out our R. No. We want to find out our amperage. Okay, so if I go E over I equals R. So we want to find out our I, so we're going to take E and divide by R. Does that sound right? And that's how I remember Ohm's law is E over I equals R, because if I can draw it out, then I can see the math formula in my head. So I'm coming up with E, our voltage, is 9. And we divide by R, resistance is 1.9 to find out our amperage. Anybody want to share their answer? I got mine.
4.7368.
Yep, that's what I got, exactly. Anybody else get anything different?
That's what I got.
Yeah, and like I said, I apologize for, I mean, I guarantee you, if any of us have any kids or grandkids in junior high school, they could have probably run circle across all of us doing this math, but I know they could have run circles around me. But I like to do this because I think it shows a really cool correlation between things. So why would a digital volt-ohm meter not be useful to check the resistance of a bulb being used in the circuit? If we take this last circuit that we just did, then we had a 4 ohm bulb, 6 ohm bulb, and a 10 ohm bulb, which probably wouldn't happen in the real world, but why would a digital volt-ohm meter not be useful to check the resistance of the bulb being used in that circuit? Anybody want to take a stab at that one?
Was the bulb on?
Well, now back to fundamentals from last week. We wouldn't want to be measuring resistance of a circuit if there was power applied to it.
Right.
Okay, so I'll kind of fill in some pieces here. If we measure the resistance of the total circuit, we should get 1.9. That's what our math agreed to, right? So if we disconnected the battery and where the two wires that would hook to the battery for this circuit, again, we're doing the exercise 3 where we had one 4 ohm, one 6 ohm, one 10 ohm. We should measure 1.9 ohms for the whole circuit because that was our total resistance. Everybody agree? Anybody disagree? Okay, so the question is kind of a tricky one. The students like this one when we're doing all this hands-on and they've got their meters actually out on this circuit. And the question is, why would a digital volt-ohm meter not be useful to check the resistance of a bulb being used in the circuit? Well, if it's in the circuit and we're measuring the resistance, we're going to get the total resistance of the whole circuit, 1.9. So an effort to see what the resistance is of each bulb, what would we have to do? We would have to actually remove the bulb from the circuit and measure each one individually. Now, if one bulb by specification is supposed to be 4 and the other one is supposed to be 6 and the other one is supposed to be 10, if we know that that's all that's in the circuit and we want to work the Ohm's law formula, let's say the manufacturer on the circuit we're troubleshooting doesn't tell us anything, we can actually say, yeah, hey, we've worked the math. We should see 1.9 for the whole circuit. So we can use a meter and answer the fact that, hey, we got 1.9 ohms for the total resistance of the circuit. But then if we have something different from that, then that's the point where we have to come out and start pulling the bulbs and check each bulb individually. So I kind of like that question. We have a lot of fun with it. How could the resistance of the bulb be determined? Well, the answer is to remove the bulb and measure the resistance individually of it. And that goes back to what we talked about last week. It's hard to measure, or it's really impossible to measure the resistance of a component in a circuit when it's in a circuit. You need to take it out. Let's see. I think my number 6 is misaligned. I think that should be lined up with the N. So in exercise 3, imagine that we have a 10 amp fuse between the battery and the bulbs. Now bulb 3 burns out and is replaced by a bulb with a hot resistance of 4 ohms. What would happen to the fuse and why? That's a tough question. It almost makes you have to go back and rework the whole exercise. So we're thinking about circuit 3, and we're saying we got a 10 amp fuse on the circuit. Right now, our total amp draw is 4.7 with the bulbs the way they are. And so what we're saying is bulb 3 burns out, which was a 10 ohm, had a 10 ohm load to it or a 10 ohm resistance. and is replaced by a bulb with a resistance of 4 ohms. So if we reworked that, we could take a shortcut. We could go back. I luckily drew out all my math on this one. So 1 divided by 4 ohms is 0.25. So if I added those numbers up real quick, let's see if this proves what I might have been trying to prove. I'm sure it does. 0.25 plus 0.25 plus 0.1666667 equals, ooh, that's an evil number, 0.66666667. Divide that by 1 divided by 0.66666667
Basically
equals
getting 13.5 amps in.
1.49. Yeah, that's where I'm kind of leading. So 1.449. I think I'm working this right. I don't know. The 9 divided by 1.49. I came up with 6 amps, but I probably worked something wrong because I was kind of rushed. What did you get, Lester?
I'm probably wrong. For some reason, I come up with 13.4993.
Well, I think I actually think you're right, Lester. Did anybody else work it out?
I got 6 amps for the final.
Anybody else get anything different? Lester, what did you do? You took 1 and divided it by 4.
Right.
And then
So
you took 1 and divided by 6. And
right.
then you took 1 and divided by 4 again, right?
Right.
All right,
Came
so
up
you
to
added all those numbers up, and what did you get?
0.6667. So 9 volts.
0.6667.
67.
But you got to do the 1 divided by.
So now you take.
I didn't do the 1 divided by 3. Yeah,
Yep.
okay. Or the 0.667.
Now the rest of it should be just from that point. It should be 1 divided by 0.6667. Agreed?
Oh.
If we're working our math out right. Let's try it again. 1 divided by 0.6667. I still got virtually the same answer, even though you rounded it off and I didn't the first time. I came up with 1.49, which is the same answer I had before. So if I take...
That would be 6 amps. He's right.
Yeah, 6 amps. Okay. So that's probably not a good question. So maybe it is. Well, so what would happen to the fuse and why? Well, nothing. If it's a 10 amp fuse and we went from 4.7 amp load to a 6.04 amp load, nothing happens to the fuse. But I'm sure what I was trying to do when I wrote this a couple of years ago is I was probably trying to find a reason or make an explanation as to, hey, you could put the wrong resistance bulb or the wrong resistance relay in a circuit because maybe that's what you had that day on your truck, and you could all of a sudden go from a circuit that works correctly to now a circuit that is pulling too much of an amp draw. So I'm sure if we sat there and kept working this out, we could find a combination. Maybe we went from a 10 ohm bulb to a 2 ohm bulb, and maybe we replaced the 4 ohm bulb with a 2 ohm bulb. But eventually, if we lowered the resistance value of our bulbs in this circuit, we could exceed 10 amps and do what? Start blowing the fuse, right? So, yeah, like I said, I mean, what's cool about this is, well, I don't have the right bulb. Can I get by with putting it in? And, if you know the circuit and understand it, you can make a determination by running the same calculation and figuring the answer to that question out. Or maybe the question is, well, my mechanic didn't have the right resistance component, whether it be a bulb or whether it be a relay, and he replaced it with this one. It should have worked, but now we're blowing fuses all the time. Here we go. We got kind of a formula for it. And this is where I'll pause and I'll ask the guys in the class to raise their hands. Did anybody ever watch a show in the 70s called All in the Family? And there was a character in there named Archie Bunker that had a fire in his house, and he's trying to get an insurance claim. And I think ultimately they denied him because he kept blowing fuses in his fuse box. And apparently it was one of the old fuse boxes that used the screw-in fuses. And instead of fixing what was wrong with the circuit, he stuck a penny in the fuse box and screwed the fuse down on top of it. So I don't know. That's my joke for the day. But that concludes this section. A little bit kind of topsy-turvy to some degree here and there with what we were doing today. But hopefully what we've learned is parallel circuits. We've used Ohm's law a little bit in the exercises, and on a series circuit we can total the resistance in them. In the parallel circuit, if the resistance values on each leg of the circuit, and we know how many legs are in the circuit, we can divide as long as the resistance is the same. If the resistance on each leg of the parallel circuit is slightly different, then we got to work out this fun formula. I will say that if you go somewhere online, they have these little online calculators that you can just enter the values in and the number of legs you have, and it'll do the calculation for you. But I think it's a little fun to challenge all of us to make us work out the math. But from here, I'm going to do what?
You should have opened with that.
I know. But like I said, this is just understand that I encourage you, if you want a copy of this, I'll be happy to email you a copy of this. And if you want to go and get a breadboard and play around with it, or if this is where I wish I had grandkids now, but I don't have grandkids period, but I wish I had grandkids that were old enough to sit down and play with them on stuff like that, because you could sit down and spend hours of fun with a breadboard and a little electronics kit building these circuits, and not just playing with them and having fun, but doing some practicalities to them to help the kids understand what's really going on. But if you're like me, anytime you were teaching the young kids, you're always learning yourself too. So with that, I'm going to conclude and open the floor up for just open discussion or any questions. And I do believe we come back on October 16th. We're going to get into the really fun part, which is we're going to talk about relays and semiconductors. And then the following week on October 23rd is where we take all of these sections and we put it into some practices with actually kind of reading and troubleshooting schematics. And what I'll volunteer on that day is kind of like we'll put some example schematics up on the screen, and I'll kind of do my best to throw up some scenarios of problems that we could happen or have, and I'll tell you how I'd go about troubleshooting it to try to narrow things down a little quicker. And I'm not saying we're going to use any of this math and that troubleshooting. Again, these sections were developed as part of the class more to help the students learn how to correlate a schematic and how to build a circuit off of it. But it was also to understand how Ohm's law works.